Hello and welcome back. Today we are going to talk about buoyancy and the Archimedes principle. So this is an object that is submerged in a fluid. There is a net force on the object because the pressures at the top and the pressures at the bottom are slightly different. The buoyant force is found to be the upward force on the same volume of water. So, an implication of this, everything in a fluid has a buoyant force acting on it. Objects sink in fluids not because they're not buoyant, but simply because the buoyant force acting on them is less than the gravitational force acting on them. The net force on the object is then the difference between the buoyant force and the gravitational force. The Archimedes principle gets its name from the parable of Archimedes and the king's golden crown. Archimedes was actually able to determine the difference between a fake crown and the real one by knowing that the density of gold, and thus being able to show that the fake crown was indeed a fake. So, if the object's density is less than that of water, there's going to be an upward net force on it, and it's going to rise until it's partially out of the water. In the case of ships, this upward force is often so great, because it's mostly air that's actually being pushed underwater, and air has a very low density, that a very dense ballast is often used, such as stones or metal ingots, to keep the ship from being top-heavy above the water and tipping over. So, for floating objects, the fraction that is submerged, just the fraction that's below the water line, is given by the ratio of the object's density to that of the fluid. In other words, if you have a log that is 100 kilograms per meter cubed, and you have water, which is 1,000 kilograms per meter cubed, you're going to get 1/10 of the log underwater and 9/10 of it above water. This same principle also works in the air. This is why hot air and helium balloons rise. The air or the helium inside the balloon is actually much less dense than the surrounding air that it's in. So let's hit a problem real quick. So we have a crane which is lifting an 18,000 kilo steel hull ship out of the water. So we've got a wreck in the water. Determine first the tension in the crane's cable when the hull is submerged, and second, the tension when the hull is completely out of the water. So when the hull is submerged, both the buoyant force and the tension force act upward on the hull. And so their sum is equal to the weight of the hull. The buoyant force is the weight of the water being displaced. If we write that out and we solve it for tension, going to go ahead and plug in a few variables. It looks like we're not given enough info to solve at this point, so we should probably break this down into components. I obviously can put my buoyant force into density, volume, and gravity. There's no really good way to know the volume of a steel hull. Or maybe I could break my volume down into mass over density, because I know my steel hull is going to be some odd shape that nobody will ever be able to figure out. And then I can go ahead and rearrange this and see if I now have enough info. Do I have the mass of the hull? I do. I know the density of water. The density of the hull, I can go and look up steel density in the book. I'm good to go, so let's plug in some numbers. And it looks like our wreck when it's fully underwater, there's going to be a tension on the line will be about 154,000 newtons. So when the hull is completely out of the water, the tension in the crane's cable is going to be equal to just the weight of the hull. So the tension on the line is going to be about 177,000 newtons. No buoyant force when it's above the water. Well, that's not entirely true. There's a very, very small buoyant force, but the density of air is so small that the buoyant force pushing it up is practically negligible. So thank you for watching. Please remember to check as you learn for the rest of your assignment.